Yes, okay. In previous class, we have learned a lot of algorithms to solve economic dispatch, such as lambda iteration algorithm, the gradient-based algorithm, and we also learn a very good method called Newton's method. Newton's method has a fast convergence speed. In the end of that class, we have learned the Newton method like this. If we want to solve a problem, or we want to solve the root of delta Lx equals 0, what's delta Lx? This is the first order derivative of the Lagrange function. To solve economic dispatch, is equivalent to solve the root of this delta Lx equals 0. So based on Newton's method, we have this. Delta x equals the first order derivative of delta L, and then inverse multiply delta L. What's delta L? Delta L is the first order derivative of L. Okay, you should know the meaning of delta L. Okay, the meaning of delta L. The delta L is the first order derivative of L over dxi. What's xi? Xi could be means p1, p2 until pn, and also lambda. So pi stands for this. So delta L means d means the first order derivative of L over p1, p2 until lambda. So delta L is a vector. Okay, is a vector. Is a vector. Can you hear me? I just found there is a problem for the internet. Can you hear me, please?
Yes. Now.
Yes, 老师.
Okay.
Hear you now.
Okay. Sorry. Okay, let's continue. Okay, let's continue. So if you have a vector, then the first order derivative of this vector, you will got a matrix. Okay, it's a matrix. The first order of this vector, you've got a matrix. The matrix will be the second order derivative of L. The element in the first row will be delta L over x1, x2 until xn, and the last will be lambda. Okay, you can similarly calculate the element in the second row until the n plus 1 row. You will got this. Okay, so if we have an expression like this, you can easily calculate the second order derivative of L over p1. You will got this. Okay, you will got the first element will be this. The second column in the second row and the second column, and this will be -1. This will be -1. Why? You can calculate based on this. If you calculate the first order over lambda, and then the first order over pi, there will be -1. Okay, so you get this. Okay, if you calculate the second order of p1, if you have an expression like this, f1 a plus bp1 plus cp1 square. What's the first derivative? What's the second order derivative of this? You will of course got to see. This is the second order derivative. Okay, based on this. Similar for this, you will, for example, this a1, b1, c1. You also have an expression as a2 plus b2, p2 plus c2, p2 square. You will got this. Okay. Similarly for generator 3. Okay. So you can easily calculate the h if you have like input-output curve like this. Okay. So based on this, I have shown you example. For example, this will be this column for A, B, C. Okay. This from P1, P2, P3 means that this is for generator 1, generator 2, and generator 3. Okay. This A1, B1, C1. A2, B2, C2, A3, B3, C3. Okay, so based on this, we have used the MATLAB to code this lambda iteration. The key part is this. The key part is this part. Okay, you should know the meaning of this. Okay. I will not repeat this. And if you have any questions, we can discuss after class. Okay. So until now, we have learned many algorithms to solve equivalent dispatch, just as I mentioned, the lambda iteration method, the gradient-based method, and the Newton method. You find that there is one characteristic that all these methods based on the derivative calculation. Either you have to calculate second order, or you have calculated the first order. Do you remember? Yes, here, first order. And also for lambda iteration method, you have to calculate the first order. Yes, you have to calculate the first order. So to sum up, all these methods are based on their derivative calculation. Means that you have a convex input-output curve, and you can calculate the input-output relationship and their derivative. So this is the common features of this method. Okay, in this class, I will show you some special method to solve some equivalent dispatch, which doesn't have the derivative. Oh, okay, all the derivative is not continuous. Okay. So let's continue for equivalent dispatch. Lecture 3. So in today's class, we will learn the method called dynamic programming method to solve equivalent dispatch. As I mentioned, for lambda iteration method or gradient-based methods or Newton methods, they are all based on derivative calculation. However, for dynamic programming, we don't rely on the derivatives, so it's very useful for some special equivalent dispatch problems. Let me have a look. For example, if you have the input-output curve like this, you will find the first order derivative is constant. If you have multiple linear input-output curves, you will find the first order derivative will be some unsuccessful time point. Means that there is jumping between this range and this range. So that means that there are 7 different values for the first order derivative. So for this type of equivalent dispatch, or for this type of input-output curve, you can't use the derivative-based method, because for the derivative-based method, when the first order derivative of all the generators are equal, we found the solution. We found the ultimate solution. But for this, you can't find the equal first order derivative. So you can't use the derivative-based method. We will use the equivalent dispatch solved by the dynamic programming method in this lecture. Okay. So piecewise linear cost function can't be used with gradient-based optimal method, like the lambda iteration method or gradient-based method or Newton methods. Such methods will always land on p minimum or p maximum, because the first order derivative of this input-output curve is constant, or with several different points. You see, this is one value, second value, third value. It's a lot like a linear equation. And you
Laoshi, your voice
if you have
distortion.
okay, sorry, because there is some a single distortion for my internet, so I always try again and again. Okay, so that's all. I found the single is better now. Okay, so you still remember if we have an input output function like this, a plus bp plus cp, we will have an input output curve like this is a square. Okay, is square. Then the first order derivative will be a linear. Okay, is a linear. Okay, is a linear. This is for f. Then we have the first order derivative will be like this: b plus cp squared. Okay, we will have 2 multiply c plus p. So you found that is a linear equation for the first order derivative. So based on this, we have calculated the optimal solution by lambda iteration method, gradient based method, or Newton method. All these methods based on the first order derivative. Okay, when we found the solution, the first order derivative of all the generators are equal. This is the finite meaning of the derivative based method. However, for this method, for this special input output curve, we can't use this method because we can't find the equal increment cost for all these generators because the increment cost is jumped or they are not continuous. Okay. So a table-based method resolve this problem. And we will find all units, we will run in all units, begin to raise the output of the unit with the lowest increment cost segment, means that we will run the generator, run the cheapest generator first. After this generator is falling and ran up, then the second cheapest generator will be turned on. Okay. So if this unit hits the right hand and our segment or hits P maximum, find the unit.
Laoshi, we can't hear you continuously.
Okay. Okay. I'm sorry, the internet is not good today.
Laoshi, your network connection is not good, so we are unable to hear you continuously.
Oh yeah. Yes, I always, yes, the internet is not good today. I always try to recollect the internet, and so there are always some interruption for our presentation.
Laoshi, is it recorded?
Sorry?
I mean, is it recorded lecture? Like previous, you have recorded 2 to 3 lectures. Because we are not understanding it continuously.
Okay. Yes. If you have the Tencent app, you can use the Tencent app. I think it's better because their cut-on by always disrupted by the internet. Oh, okay. So let's continue. So for this for this dynamic programming, we first run the most cheapest generators and then run the second cheapest generator. And like this, we turn on the generator one by one. From the most cheapest to the most expensive generators, we will find the optimal solution to solve economic dispatch. Okay, so eventually the total of all units output equals the total load, means that we turn on the generator one by one. First, we turn on the most cheapest generator, then we turn on the second cheapest generator. Just like this, at last we turn on the most expensive generator to support the node. Okay. So the last unit is just to have generation, which is partial node for one segment. That means maybe the total generation of all units is not exactly match the total load. So for the last generator, maybe the generator only have to generate partial output Okay, that means the last generator may be not lesser to use up. It's our capacity. Okay. So so we use dynamic programming to solve many kinds of problems. This problem has a feature that they don't have their continuous derivative. So we use dynamic programming to solve this problem. DP means dynamic programming. DP applications can be developed for economic dispatch or can used for intercommitment. We will learn this problem later. We can also solve the hydrothermal scheduling. Okay. These methods are introduced. I will introduce methods by presenting examples. Okay. And that means I will show you a mathematical problem, very simple problem first, and you will know what's the meaning of dynamic programming. Okay. That means that, okay, here, when you from point A and you want go to point N. So there are a lot of paths you can choose. Travel from point A to point N. But for each path, there is a different cost. There's different cost. Maybe this is the time cost or traveling fee cost. It doesn't matter. I just want to tell you that if you choose different paths, the total cost will be different. So our problem is that how to find the most economic path, or you find the path with the minimal cost to travel from A to point N. Okay, that's our problem. Okay. Any question for this? First, you should stand. Okay. You should stand. What's the problem? We have start from A and want come to point N. And there are a lot of different paths. Maybe such as you can travel like this: A, B, E, H, L, N, A, C, F, I, L, N. Okay, there are a lot of choices you can choose. But for different paths, there is with different cost. Maybe this time cost or travel fee cost doesn't matter. Your objective is find the minimal cost to travel from A and to N. Okay, this is the problem. Okay. So consider the cost of transporting unit from location A to location N. There are many short paths that collect many stops along the way, which offers numerous parallel routines from A to N. Each path has an associated cost. That means this is the associated cost. Okay. So the total cost is the sum of paths you choose to go from the point A to point N. So the problem is to find the minimal cost routine. Okay. So you know our problem. For each path there is a cost, and you want to travel from A to N and find the minimal cost. So you determine which path you should choose. Okay. This is our problem. So there are various stages. So there are various stages traversed, means that you can choose. There are many choices. You travel from N to N, A to N. There are a lot of choices. Starting at A, the minimum cost path to N is ACELN. Okay. At this step, you don't have to know how to get this. I will show you how to get this. Assume that we have found the best solution by this method. If you list all the costs, all the paths, for example, you list all the paths A, B, E, H, I, L, A, B, E, I, L, N, A, B, C, F, I, L, N. You list all these costs and you compare all these paths, you will find that ACEILN is the most economic one path, or this path is with the minimal cost. Okay, we just want to observe some conclusion from these results. Don't worry, I will show you how to find this. Okay. Starting from A to N, you will find the best course is ACEILN. When you start from C to N, if you from C to N, after you list all the paths, you will find the best path is CEILN. And from you starting from E to N, you will find the best path is. If you travel from C to N, you will find the best path CEILN. You travel from E to N, you will find the best path EILN. Okay, and similar for ILN. Okay, so based on this, you can observe some conclusions. That means the choice of routing is made a sequence, and this is the suboptimal, or this is part, or this is just a part of the best path. You will find that the optimal sequence is called optimal policy. It means that if you travel from A to N, we call this is the optimal policy. If you travel from C to N, we also call this the optimal policy. That means that this all optimal policy, but CEILN is just a part of this, so we call this is the sub policy. Okay, so the optimal policy, the whole optimal policy from A to N will contain only optimal sub policy. Means that the best path will of course cause the best segment of the sub policy. Okay. So don't worry how to find this path. I will show you. I just want to give some conclusions based on this observation of you. Okay. So divide up the field of paths into several stages. For example, for this we will develop this problem into 5 stages: stage 1, stage 2, stage 3, stage 4, and stage 5. This is one stage. This is another stage, 3rd stage, 4th stage, and 5th stage. Okay. So develop the path into several stages. At the terminal of each stage, there is a set of nodes. That means there is some choice you can select. For example, at stage 3. What's the problem for internet?
We can't hear you properly.
Yeah. Okay. When the internet doesn't work, I stop speaking. So after I recollect internet, I will continue speaking. Don't worry. You won't miss anything. Okay. Sorry. Okay. Okay. So for example, I mean that for this problem, we can divide this problem into several stages, where stage 1, stage 2, stage 4, stage 4th, and stage 5th. For each stage, there are different points. That means you have different choice. For example, if you travel from A to the 1st stage, you can stop at B, stop C, stop D. So for each stage, there are different stops. Okay. Also for stage 3, you see there are different stops. H, I, J, K. This is a different stop or different points. Okay. So at the terminal of each stage, there's a set of nodes or stops or points, right? Or points. So at stage 3, the stops are H, I, J, K. Okay. A set of courses can be found for crossing a stage. For example, you travel from stage 1 to stage 2. You travel from this to this. If you travel from point B in stage 2 to point E in stage 3, the course is 11. Okay, the number above the arrow is the cost. Okay, so that means if you travel from point C to E, means you travel from the second stage to the third stage, the cost is 8. So the number in this figure, it means the cost you travel from one point to another point. Okay, what's the meaning of this number? Okay. So a cost, so a set of costs can be found for crossing a stage. Means that you travel from one point from stage K to stage K plus one, there will be a cost. Okay, a cost is dependent on the starting and terminals of a stage. Okay, so you can find that if you travel from E to H, or you travel, their cost will be 3. E to H, you see 3. Okay, you will travel from F to I. There will be 11. Okay, you can turn back. F to I 11. Okay, so let's continue. So the minimal cost for traveling from stage 1 to stage I and arrive at some particular nodes or particular stops is defined as this Fi, F1, Xi. So the minimum cost from stage 1 to stage 2 for loads B, C, D. Let's show how to calculate this. Okay. If you travel from A to this stage, if you travel from A to B, the cost will be 5. Travel from A to C, the cost will be 2. Travel from A to D will be 3. Okay. Let me, you see, you travel from stage 1 from A to B will be 5. A to C will be 2. A to D will be 3. Okay, that means you travel from stage 0 to stage 1, you have different costs for each stop. Okay. So let's continue. If you travel from stage 1 to stage 3, what's the cost? Means that we continue for the next stage. We have already calculated from stage 0 to stage 1. Now you have calculated from A to this stage. What's the cost? Okay. Okay, what's the cost? Okay, also in this figure, we have recorded the cost for each stop. Means that you travel from A to B, the cost is 5. We just the red number here in the circle. Okay, and in the circle. Okay. So based on this number, we know that from A to B 5, A to C 2, A to D is 3. So we want to continue to go to the next stage. So if you in stage 2 and you want to go to point E, so there are 2 possible paths. You can from B to E or C to E. Yes. So if you from B to E, the cost will be 5 plus 11 will be 16. If you travel from C to E, the cost will be 2 plus 8. So the cost, this path is better. ACE is 10, ABE is 16. So this is better. ACE is better. We just record the better one here. Okay, so we just write the number 10 here. For this 10, you know that the number is for this part, ACE. Okay. Similarly, if you travel to point F, this can be ACF or ADF. For ACF, the cost is this number multiple plus this, so it's 2 plus 4 equals 6. Okay, I just read here. If you read this, will be 6. Okay, this number plus this will be equal 6. If you travel from this ADF, because for D point the minimum is 3. 3 plus 6 equals 9. Okay, so if you travel C to F will be 6, D to F will be 9. So the better one is this one. Okay, so we just record the number here, 6. Okay. Similarly, we calculate the stop G. You will find 2 plus 9, 11, 3 plus 6, line. So this is better. Okay, D to G is better. So that means for point E, we have a solution that ACE. For F, we have a solution ACF. For G, we have a solution ADG. Okay, so and for this stage, we have already know from travel from A to E, the best solution is 10. A to F, the best solution is 6. A to G, the best solution is 9. Okay, so that means we have already arrived here, arrived this stage. Okay. Okay. Our problem is that we want to write this stage. Okay. So let's continue and repeat this procedure. So if we go to the next stage. Okay. Next stage there are 4 stops. So if you arrive H, how to get H? You can from E to H or F to H. If you choose from E to H, because the cost from E to H, the crossing cost is 3. So the total cost will be 10 plus 3 equals 13. If you travel from F to H, because here the best cost is 6, so will be 6 plus 8 equals 14. So this is smaller than 14. So you travel to H, this path is better. So for H, the best cost is 13, and the path you know will be E to H. How to get E? Of course, C to E. Yes, and how to get C? AEC. So the best path will be like this to H. Okay. Similarly, we can calculate the best cost for I. That means how to get from A to I. The best cost, we will find that 10 plus 2, 12. 6 plus 11, 17. So the better cost is 12, and the path is E to I. Okay. Similarly, calculate G. G from I to J will be 11. Okay. There is no other path to this point. So the best path will be F to G. So the best path will be F to G and ACFG. Okay. For point K, if you travel from point F to K, will be 6 plus 9, 15. If you travel from point G to K, will be 13. So the best path will be this. Okay. Here, this path will be this. For this, the best path here. Okay. For this, the best path will be here. Okay. So let's continue. After we calculate, we know that the best cost for stage 4 is H is 13. What's the meaning of 13? Means that you travel from A to H, the best cost is 13. You travel from A to I, the best cost is 12. You travel from point A to J, the cost is 11. And you travel from point A to K is 13. Okay. What's the meaning of this number? Okay. So continue for the next stage. Okay. For point L, you can have 3 possible paths. From H to L will be 22. For I to L will be 15. From G to L will be 18. 11 plus 7 will be 18. So the best path will be here. Okay. Best path will be here. Means that for L, the best path will be here. Okay. For M, there are also 3 possible paths. If you travel from I to M, will be 18. Because 12 plus 6. From G to M will be 19. Okay. From K to M will also be 18. So that means there are possible 2 possible paths here. Okay. So that means these 2 paths are the same, or have the equivalent, or have the same cost. So for L, you have the best path from I to L. From M, you have possible two paths, I to M or K to M. It's okay. They have the same cost. Okay. So last, we travel from stage 5 to the last stage. Okay. If you travel from L to N, the best cost will be 15 plus 4 will be 19. Okay, if you travel here, 19. If you travel here, 21. So that means this is the best path. Okay. So that means how to travel to N? You should choose from L to N. Okay. But how to travel to L? You know the best path is I to L. Okay. How to travel to I? The best path is E to I. How to travel to E? The best path is here. C to E, and the best path is A to C. So the fellow you found the optimal path will be like this. Okay. I, N. So this will be the best path. Okay. And so let's repeat our procedure. First, we have to calculate the fuel cost calculate the cost for each stop, for each stage. For stage 1, we should remember the best cost for each stop and the best path. Okay. Then we continue for the second stage. Second stage, how to get E? There are different paths, and we only keep the best path here. Okay. Best path is ACE, and the best cost is 10. Okay. We just repeat this, and we've got the final destination and to N. So the best path will be ACEILN. So any question for this part? I just show you how to use dynamic programming to solve this mathematical problem. Okay, that means we have start from A to N, and there are different paths with different costs. How to find the best path? Okay, we just solve the problem one stage and another stage and continue to the next stage. Okay, any question for this? It's a very simple mathematical problem. We calculate the stage by stage and found the best route is ACEILN. Any problem for this? I have already opened your voice. Okay, I have already opened your voice. You can also type the word here, because you can type words here in Ketanpai.
No questions, sir.
Oh, okay, no question. Okay, thank you. So at each stage, the minimum cost should be recorded for all the terminal nodes. I have already conduct these steps for you. You will travel from A to B, the cost 5 to A to C will be 2, and A to D will be 3. And you continue for the second stage. If you travel to E, the best path will ACE, and F also ACF. G will be ADG. Okay, you continue for the next stage. For stop H, I, J, K, you also record the best course and the path. For L and M, you also record the path. Actually, for 18, there are 2 paths, ADGK. You see, there will be, because you can travel from K to M and also from I to M. So ADGKM, or you can travel like this, ACEIM. Okay, this 2 paths has the same cost. Okay, has the same cost. Last, you arrive at the point N. You will got the best cost is 19. The best path is ACEILN. Okay. So in this during this in this procedure, you found that we don't use the derivatives. As I mentioned earlier, for the lambda iteration method of the Newton method or the gradient-based method, we always have to calculate the first order derivative. To solve this problem, you found that we don't calculate the first order derivative of the function of the input of the curve. Yeah, we just compare some possible paths and found the best path. Okay. So In this example, I just show you how to solve a mathematical problem by dynamic programming. Next, I will show you how to solve economic dispatch by dynamic programming. Okay, economic dispatch when the heat rate curve exhibits non-convex characteristic, it's not possible to use an equal increment cost method to find the best solution. We will use dynamic programming from the ordinary dispatch and such circumstance. For example, if you have an input-output curve like this, and based on this, you can calculate the first order derivative of the input-output curve. You will find the increment cost will be like this. The first order derivative is very complicated. It's not like this. It's just linear. It's just linear or square. These two types is continuous, and for this type, there's some jumping here. You see, they are not continuous. Okay, so for this type input output curve, it's difficult to use the derivative-based method. So we will use the dynamic programming method to solve. Okay. Okay, in next, we can have a 5 minutes break, and after 5 minutes break, we will continue to show how to use the dynamic program to solve economic dispatch. Okay, during this break, if you have any question for this, you can discuss with me. Okay.